Dignitaries, jury members, and delegates, and all present here, a very good afternoon, all of you. I am Ramashu Bhavakar. Good afternoon. I am Ramashu Bhavakar and I am going to present my study ultrasonic and thermophysical properties of binary and ternary alloys of transition metals, titanium, zirconium, and hafnium. My co-authors are Mr. Shakti Yadav, Dr. Viral Mishra, and Professor Devraj Singh. Next, please. These are my outlines of the presentation: abstract, introduction, theory, second order elastic constant and third order elastic constant, ultrasonic velocity in different directions, elastic properties, thermal properties, attenuation, and conclusion. Next, please. This is my abstract. I have calculated work modulus, shear modulus, Poisson ratio of these alloys, and I have also calculated the specific heat at constant volume of these metals, and also attenuation. Next, please. Introduction. So these metals are refractory high entropy metals. Refractory means those metals which are shows high resistance to heat and wear. Means that they are stable at high temperature and high pressure. So these are the metals: titanium, zirconium, hafnium, niobium, tungsten, molybdenum, and titanium. You must know that here I want to emphasize that the nozzle of the Apollo lunar modulus engine C103 consists of these alloys. So this is important for our study. Next, please. This is the theory of my calculations. So we have incorporated the Reynolds potential parameters for calculation of SOEC and QACs of these metals. Next, please. These are the formulas of these parameters. Here the P is the CY-axial ratio, that is this upon the basal plane distance. These are the Reynolds parameters, but it is very complex to calculate these parameters. So we have used already available data of the C3 in literature to calculate these parameters, and then these parameters were employed in calculating all these parameters. Next, please. These are the velocities of ultrasonic velocities in different directions. Okay, we have taken the unique axis of the SAP 100 at this, and we have calculated velocities, longitudinal velocity, partial shear velocity, and shear velocities, and then we have found the dy average velocity. These are the formulas. Here theta is the angle with the unique axis, and these are the C3 and C11. All other are the second order elastic constants. Okay. पीछे जाइए. Okay, okay. Okay, now after finding the dy velocity, we found the dy temperature and then Cv. Next, please. These are the formula for attenuation. Here E0 is the thermal energy density, and tau is the thermal reaction time. Gamma is the other numbers which are calculated in 41 different directions, and then average and squared for using the formulas. Next, please. Okay, these are the results. We have calculated the SOECs of the different materials. Here we have shows the metals materials, and here are the in magnitudes of the SOECs. Okay, I want to going to notice that here okay, C112 is nearly same for all the metals, but if we see C111, there is a significant difference between them. And also these are the conditions that these follow. So we can say that they are mechanically stable. Next, please. Okay, these are the velocities with the angle, and okay, for different metals. Okay, longitudinal velocity is lowest at 40 degrees and highest around 90 degrees. Okay, and similar. Okay. Okay. These are the Cauchy shear velocity and shear velocity, and these are the desired average velocity of these metals. Next, please. Okay, these are the moduli, elastic moduli of the metal. Okay, TiZr material shows 95.15 gigapascal. Maximum is for TiHF, which is 1.107.32, and it also shows the Poisson ratio of 0.28, which is important because the more is the work modulus, more is the stiff material. Material is more stiff, and if we elongate the material, it shows that the 0.28 of Poisson ratio shows that we have to extra pull to elongate them. Yes, please. Okay, these are the lattice thermal conductivity of these metals, and with angle dependence. Next, please. Okay, this is the specific heat capacity TV. Okay, this is plotted on a bottle temperature. We say that TV rises with temperature, but with significant rise in temperature, TV becomes constant. This shows that these follow the long-Peter law. Next, please. Okay, these are attenuation. We see that the attenuation due to longitudinal mode is this, and shear mode of vibration. This shows that this nature of the here the on 0 degree, these are higher, and on the 90 degree around they become very less. I will also emphasize that with increase in temperature, with increase in temperature, the attenuation of due to longitudinal wave increases, but the thermal luxation due to thermal luxation become nearly constant. Next, please. These are my conclusions of the result. Here it shows that due to SOCs and these conditions, we can say that the alloys are mechanically stable on higher pressure and temperature. We can also say that the desired average velocity is the highest for TiZr at 3.6, which is 3.62 in per 3 meter per second. For TiHF, the work model is found to 107.32 gigapascal, which is highest in my study. It shows that this is the stiffest material. Okay, and also I have also mentioned that TV follows the DeLong-Peter law at higher temperature, which is the DeLong-Peter law is actually which says that at higher temperature, most of the series of the metals become constant. Okay, these are okay. I have also considered that the ultrasonic attenuation longitudinal mode vibrations are much higher than the shear mode of vibration and thermal reflection vibration. Vibration. Okay, longitudinal vibration mode of vibration are resultant due to phonon interaction, but the thermal reflection mechanism is involved with the electro. Sorry. Here are my references. Any question, please?
Thank you. Now, the paper.
Theoretically. Yes, sir. We didn't use any. We use the Lennard zone potential model for this, and I have programmed whole process in Python for these calculations. Ternary? The TIHF ZR. Any question? कल तक होता है वो उनसे दिरा सिंह आ रहे हैं अपने वो लोग आ रहे हैं तो उनसे मिलना चाहिए
Good afternoon, everyone, respected teachers and all dear students. Myself, Prashant Kumar Shinde, and today my paper topic is evaluation of intrafraction 6D residual error in spine stereotactic body radiotherapy and brain stereotactic radiosurgery. Analysis with kilovoltage cold-beam computed tomography. Basically, this topic is related to the radiation therapy. So, introduction in modern radiotherapy, spinal and brain metastasis. Metastasis is when cancer spreads to a distant site from primary, it is called as metastasis. So, in spinal and brain metastasis are treated with hydrofractionated stereotactic body radiotherapy and stereotactic radiosurgery. So, SBIT and SRS are planned with the state-of-the-art radiotherapy techniques like intensity modulated radiation therapy, volumetric modulated arc therapy, in which the radiation dose is delivered when the radiation is moving along the body. So, SBIT are treated with 1 to 5 fractions and SRS is treated in single fraction. So, you can see there the dose is in this dose is highly conformal to the target, and beyond the benefit of target there is a rapid dose follow. So the position of patient at the machine is very vital and accuracy is highly appreciable. So for accurate treatment delivery, therefore essentially a small change in patient position can transfer a significant dosimetric impact to the adjacent normal tissues. So even if the patients are immobilized with the rigid immobilization, even though there are some small variations in the patient positioning. So with the use of kilovoltage quantum computed tomography, which is on board on the machine, or verification imaging is taken and the corrections are done so that the proper radiation treatment will be delivered. And the combination of 60 cows is also vital. Using 60 cows, all 6 dimensional errors can be corrected when the treatment is going on. So, however, with the combination of these, on phantom studies, accuracy of 0.3 millimeter and 0.3 degree is evaluated in the phantom studies. However, in the patient, there are multiple factors. So, these accuracy needs to be evaluated in the actual patient treatments. So, the aim and objective of study was evaluation of interfraction with the residual error in spine stereotactic body radiotherapy and brain stereotactic radial surgery using kilovoltage cone beam computed tomography and 6D robotic couch. So material method, this retrospective study included 15 spinal metastasis patient and 15 brain metastasis patient treated with SBRT and SRS respectively. So this in this figure right hand side you can see that upper figure that is showing us spinal nets. Here this is a malignant tumor in the spine bone, and inside the brain there is a malignancy inside the brain. So these patients were treated with 27 to 30 grain SBRT in 3 to 5 fraction, and the brain patients were treated with SRS of 18 to 21 grain single fraction. So the patients were planned. So patients were planned, and this you can see the dose distribution here in the spinal case SBRT and SRS. So high dose is delivered in a single fraction in SRS. So the patients were planned with the IMRT and the VMAT treatment technique on variant Rubin linear accelerator. This is a linear accelerator which is having a mega voltage photon energy. So the patients are treated with the mega voltage photon energies. And this is a triple A beam which is 6 MB photon energy plan for SRS and SBRT. And the patients were immobilized. So SBRT spine patients were immobilized with a vacuum cushion. These vacuum cushions, when air is sucked out, it takes the position which is given to the mold. So patients position exactly given, patient lie down here and the air is sucked out and comfortable position is given, and the patient position will be reproducible. However, in brain SRS, a 3 clamp thermoplastic mask is used, and this mask is very rigid, double layer. So patient cannot move, even a millimeter movement cannot be possible in this. So first scanning scan performed on the normal diagnostic CT for both the spine case and brain SRS. And then a dose calculation is done in the treatment control machine, where the model of the machine is there, and that model uses a dose calculation algorithm AAA, that is analytical anisotropic algorithm, that is used for the dose calculation inside the patient CT volume. Because CT we need electron density, and based on company interaction, air protection, and photoelectric effect, with those interactions calculated by the algorithm, and dose calculation is done. So this is the final optimized plan, which is 95% dose should cover to the planning target volume. But the critical thing inside is the spine, inside the bone. So that spine should not cross the tolerance zone. So the positioning of patient is very important. Even in brain cases, sometimes this is away from the brain stem, but when the tumor is near the brain stem, in that case also, the positioning of patient is very important. So the patient is then on machine before treatment. It is this laser is indicating the isocenter of the machine, where the all rotational motion of the machine is at that point. It is called as the isocenter point, and everything is calculated at the isocenter point. So patient should, for its target, should be reproduced at the isocenter point. So on based on body part, first they align with the laser, and then whether the patient is correct position correctly as per the plan is evaluated by taking the kilovoltage cone beam computed tomography. So on the machine there is an onboard X-ray device, X-ray tube, and this is the detector opposite onboard KV CBCD detector. So when the transmitted X-ray, this is a diagnosis X-ray, 140 to 120 keV X-rays are used. And when these X-rays are transmitted to the patient body, the transmitted X-ray are detected by the detector, and then using a backprocessing algorithm, we generate a cone beam computed image. So for brain CBCT, we use 100 kV and 270 MAS for X-ray tube, and for spine, we use 120 and 180 MAS. So patient, so the patient verification is done on the machine first. Then after that, we check whether the post correction is there, any error is there. So we take a post correction CBCT, and then there is a registration software which compare these images. You can see here this one is a CBCT image, and this faint image is a actually planning CT image. It is taken for planning. They are registered with the algorithm and each appropriate volume are matched, and then this is the blended image in the color. So after that, the software gives the correction errors in the 6 dimension in all the 3 translational axes and rotational axis. That is lateral, longitudinal, vertical, rotational, and axis. So these are the rotational axis and translational axis in the coordinate system of the linear identification. And these errors are given by the registration software, and the 6D robotic couch correct this error. But during treatment, these errors, what are the errors when treatment is going on? So this treatment is a time consuming. So the protocol we follow is that we take post correction CBCT. Then after the treatment delivery, we have the mid treatment. We stop the treatment and we take another CT that is called as the interim CBCT. How much variation is there? And then if it is crossing the tolerance, then correction will be done with the 6D robotic couch. And after that, at the end of treatment also, we took a CBCT image and we evaluate how much variation was there after the treatment. So these evaluation of these intrafractional variations are important for further planning of the patients and this. So these variation, this change in the positioning from the post correction to the intermediate treatment and from intermediate treatment to the post treatment is called the intrafractional errors. So we evaluated the mean intrafractional error in all the translational and rotational axes, and we calculated the mean 3D vector for translational axis and the average angular variation. So this is the results. So this is the mean residual error in along all translational axis and rotational axis for post correction, interim CBCT, and post treatment CBCT. So they are high. Maximum errors in translation 0.2 millimeter plus minus 0.6 in the longidirectional, and post treatment 0.2 millimeter plus minus 0.4 millimeter in longidirectional, and rotational it was along the pitch, that is along the x-axis, rotation along x-axis. So this is the frequency distribution of the errors. So greater than 0.5 millimeter errors in post correction CBCT, and all were less compared to the pre-correction CBCTs. And this is the box and whisker plot, which is giving the variation distribution error. So minimum, maximum, and mean. So these errors, the blue color represent the angular variations, and the red box and whisker plot represent the translational errors. So these errors are mean errors are within 0.2 millimeter, but however, in particular fraction, error has gone up to the 8 millimeter also, and up to the 1.3 millimeter for translational. These results are for brain cases, and the errors were less than the spine cases. This is the frequency distribution, and the point greater than 0.5 millimeter error and greater than 0.5 degree are almost negligible in the brain cases because of the demobilization. These are the box and whisker plots for error distribution. So the conclusion that the mean intrafractional distributed error in translation and rotation axis for spine, SBIT, brain, SRS were within the threshold of 0.5 millimeter and 0.5 degree. Minimal intrafraction motion is achieved by near rigid demobilization, and intrafraction CBCT imaging and rigorous positioning threshold is degree of freedom enables safe spine SBIT and brain SRS delivery. So KVCBCT represents the actual patient position during treatment and can be used for further evaluation of dosimetric impact of this intrafraction residual error on the target polymer of the case. These are the references. This is actually dose is calculated based on the photoelectric effect, combination effect, and pair production. So when photon is incident on the body tissue material, so it deposits the dose, and dose deposition occurs with this photoelectric effect, pair production, and Compton scattering. So these algorithm use the electron density inside the body, and the algorithm knows the energy of the incident photon. Based on incident photon energy and the density of the volume, it calculates what type of interaction is going to happen, and based on that interaction, it calculates how much dose is deposited inside the volume. So that algorithm is analytical anisotropic algorithm. Basically, theme of this conference is on material science and nanotechnology. But basically, it's the physics based on primary subject is physics, and my work is on physics. Basically, it involves radiation and X-ray photons and use of these X-ray photon and radiations in the clinical setting. Any questions from the audience? Yeah. There are multiple organs that's like SBRT is done in whole of the body. So body is called as the SBRT, and intracranial is called as the SRS. SRS is called because in a single fraction it is done. It is equivalent to the surgery, because when you go for operation, they have to open the brain and then they have to operate it. But it is a very traumatic operation. So instead of that, radiations are used, high radiation dose is used in single fraction, so that the tumor is destroyed and it is eliminated by the natural biological system. So the natural trauma is less.
Second. Honorable Chairperson of today's intellectual session, the International Conference, Second International Conference, Rama 2022, all respected and honorable juries, all eminent professors and personalities, all students, research scholars present over here. A very good afternoon to all. My name is Aditya Tiwari and I am a research scholar. I am pursuing my PhD from Government College, Vidarbha, from Government Vidarbha Institute of Science and Humanities, Amravati, under the guidance of Professor Dr. S.P. Yavle, sir. Next, please. Wait. And the title of my research article is
inside details of X-ray diffraction, kindly previous one. Inside details of X-ray diffraction analysis and infrared spectra of polypyrrole composite decorated with titanium dioxide and SnO2 metal oxides. Next. These are some contents. We will proceed one by one. We will start with the introduction that as our topic is related to the conducting polymers. So it is very important to note that word polymer. This word polymer, actually it is a Greek word and it is derived from two words. Poly means many and mers means chains. So polymer is nothing but a long chain of molecules which is having higher number of molecular weight. So earlier it was known that as we get a polymer in our mind, we thought of plastic. We can also imagine of polythene. These polythene and plastics were insulators, but later many researchers have studied and they came to know that there are other polymers which are conducting in nature. And these conducting polymers show very good properties, like they have very diverse structures, special doping mechanism, they have excellent environmental stability, they can sustain at room temperature, they can also have higher conductivity, and as they are having higher conductivity, they are very useful for application purposes. Next please. So let us have introduction for polypyrrole. Here we can see that this is the 5-member ring of pyrrole. When it is getting polymerized with a particular oxidizing reagent, we will get a polymer chain. Next please. This polypyrrole is one of the member of conducting polymer, polythiophene, polyaniline. These are different types of members of polypyrrole. But polypyrrole has a very significant properties than that of other polymers. It has high electrical conductivity and good properties than others. Here, my research work is based on the composite formation of TiO2, SnO2 with the conducting polymer. Why I have used this TiO2 and SnO2? Many eminent lecturers have came over here and they have shown the importance of this metal oxide when they are having amorphous nature as well as good conductivity even at the room temperature. I have been concluded from many reviews that this TiO2 and SnO2, these are only the materials they are having energy bandgap of 3.3 electron volt and 3.6 electron volt. So next please. So when they are added into the polypyrrole, some different types of composite and structural analysis can be done. Here we can see the experimental method we will come. These are the chemicals which we have required. Pyrrole is the monomer which we have procured from high media. It is to be noted that all the reagents and all the required chemicals, they are of analytical grade and research grade. Perichloride FeCl3, which is used as a oxidizing reagent for the polymerization of the reaction, and Wattman grade filter paper is used for the filtration process. Next please. Here a synthesis of pure polypyrrole and polypyrrole TiO2 and polypyrrole SnO2 composites is made. The process for this formation is very easy. One step polymerization is there, but to have this polymerization, it is to be noted that 1:2.33 ratio of polymer, monomer and oxidizing reagent FeCl3 is taken, and this ratio is chosen because it gives you the maximum yield of the product. Next thing is that 10% weight by volume of the TiO2 and SnO2 is to be added into the ferrichloride solution for the formation of composite. This is the synthesis of one-step synthesis of a polypyrrole and its composite. First of all, a beaker is taken. In that beaker, a methanol is taken, that is a 40 ml of methanol is taken. Into that, FeCl3, which is nothing but an oxidizing reagent, is dissolved into it. It is sonicated for 30 minutes. Why sonication is necessary? That to have homogeneous solution, so that polymerization must be efficient. Then, after sonication, 4 ml of polypyrrole is taken into the injection syringe, and 4 ml, and it is dropped, pour inside the material, that is reagent, drop by drop, to have polymerization. After polymerization, we all know that these all reactions are going into the methanol, and methanol is an organic solvent which is highly volatile in nature. As soon as reaction proceeds, methanol get evaporated. Due to the evaporation of methanol, oxidization potential of reaction increases, and we will get a good polypyrrole, that is paste-like paste inside the beaker. This paste is a greenish black PPT is obtained. Then this PPT is filtered, and washed properly, dried at 60 to 70 degrees Celsius in an oven, and finally black greenish powder of composites are formed. Next, please. The characterization of these composites are made with the help of XRD and IR. The X-ray diffraction technique is used, and this with the help of Rigaku miniflex X-ray diffraction, the conditions for the X-ray diffraction is maintained with the help of CUK alpha rays having angle 0 to 80 degree, and step size is 13 mm, and water flow across it is maintained at 14.3 liter per minute. Infrared spectra is obtained with the help of Shimadzu IR affinity. Next, please. We can have kind attention towards the first graph of XRD spectra of polypyrrole. Here we are having for pure pyrrole, the XRD pattern showed a broad amorphous peak at 2 theta is equal to 26 to 30 degree. This shows that this is halo nature, and it shows the long chain amorphous nature of the polypyrrole throughout the polymer matrix. And then it is doped with the TiO2. The XRD pattern shows the crystalline nature inside conducting polymer polypyrrole. Next, please. These are the results which we have obtained from polypyrrole and TiO2. Here we can see that the first three prominent peaks at 27 degree, 37 degree, and 54 degree, they are of the rutile nature of this TiO2. But when this pure TiO2 is added and get composed into the polypyrrole matrix, it changes. Rutile, 3 peaks are of rutile and 4 peaks are obtained of the anatase phase. So a conclusion can be drawn that it has been found from XRD data of the TiO2 that the ratio of anatase and rutile phases is almost 75 to 25 for the pure TiO2. But when it is getting added into the polypyrrole matrix, it becomes 57 to 43. And this indicates that the anatase phase is predominant in this composite. Next, please. This is again a composite formed with the help of SNO2. And this spectra shows that this is the diffraction peaks of SNO2. You can see this is 26 degree. It is shifted for the 26.72 degree for the composite. And all the peaks are shifted toward the higher thetas. This shifting of prominent peaks of higher peak values in XRD shifts towards higher values indicates that there is loss of conjugation of SNO2 with the conducting polymer polypyrrole. Next, please. These are the FTIR spectroscopy, which reveals the presence of interaction between conducting polypyrrole, titanium dioxide, and tin dioxide. Next, please. Next. I drawn the conclusion that the left-hand side polypyrrole absorption peaks are shown. These polypyrrole absorption peaks are shifted when TiO2 and SNO2 are composed inside the polypyrrole matrix. And the wave number peaks from 619 to 924, it shows the CH wagging inside the chain. And 1049 to 110, it concludes the CH in deformation plane vibration. And another conclusions can also be drawn. Next. The final conclusions of my topic is that the polypyrrole and these composites are made with the help of in situ chemical polymerization. And this procedure is utilized in such a way that we are getting the maximum product out of this chemical polymerization, which is very easy to obtain. These composites were analyzed by X-ray and FTIR technique. Moreover, it is found that the 2 theta values of mature peaks of TiO2 and SNO2 are shifted towards the higher side in their composite, indicate the loss of conjugation with the polypyrrole matrix. Next, the TiO2 when composed into the polypyrrole matrix, it shows that anatase phase of TiO2 is predominant. From the FTIR spectra, it is revealed that the characteristic absorption peaks of polypyrrole are shifted significantly for both metal oxide composites, indicating an existence of different interfacial interactions between these metal oxides and conducting polymer polypyrrole. Thus, it is evident to conclude that by overlapping the properties of these metal oxides and also the properties of conducting polymer polypyrrole, we can have the modifications in synthesis process towards better application. That's all from me. Thank you.
Thank you, Arvind.
Thank you.
You have delivered the presentation of inside details of the cycle analysis, and I asked about chemical composites, liquid metal, general oxide, metal oxides.
Yes, sir.
I have three. In expert metal section, now mentioned that the ideal for extraction can from 0 to 80. But your graph shows that it is 10 to 80. And now the question is whether 0 to angle is possible.
No, sir. Actually, it is not possible. 0 degree angle is not possible because actually it is 2 theta angle, and uh, that bench is set up in such a way that the 0 angle is not possible. That you will minimum angle. It is nothing but the angle of incidence actually. That minimum angle is always more than 10. It must be 10 because that diffraction is that scattering from the interfacial Bragg plane is not possible.
Anybody, if you have a question,
Yes, ma'am. Please. Yes, ma'am. Yes, yes. There are different types of oxidizing agents like ammonium persulfate is also there. It is ammonium persulfate as well as combination of FeCl3 also gives good results for the formation. But FeCl3 is eminent, more prominent. Why? Because it gives more yield. That's why I use FeCl3. Yes, ma'am. Yes. And as it is more costly, this pyrrole bottle costs more than 20,000 per me. That's why I use that FeCl3. Yes, ma'am. Yes, ma'am. Thank you, ma'am. Yes, ma'am. Ma'am, actually, these nanoparticles are not made in the lab. They are directly procured from Bangalore High Media and from Ultra Nanotech. I only have compared the structural properties of and the composite formation. I haven't prepared any nanoparticles inside lab. Yes, sir. Yes. They can be prepared very easily, sir. No problem. Yes, actually it is there, sir. But I haven't mentioned. When I have written in my paper, there is a significance of words. It must be there. It is there. Thank you so much, sir. Thank you.
Thank you, everyone. My name is good afternoon, everyone. My name is Gaurav Pradeeprao Gorle, and today I will talk about the synthesis and characterization of copper oxide nanoparticles by using. So next slide. So next. Today I will talk about the synthesis and characterization of uh, copper oxide nanoparticles using neem leaf extract. Green nanotechnology is generating interest in researchers to synthesize nanoparticles using simple, cost-effective, and green eco-friendly methods. Uh, in this study, I'll prepare the copper oxide nanoparticles by biosynthesize using neem extract. The copper oxide nanoparticles was characterized by using UV visible spectra and XRD. Next, please. Nanoparticles are ultra small size particles of having 10 to the power -9 meter size. They are highly chemically active because of their high surface to volume ratio. Many physical and chemical methods have been developed to synthesize copper oxide nanoparticles. But currently we need eco-friendly methods to synthesize copper oxide nanoparticles because of emission of greenhouse gases. So researchers are focusing on green options. In metal oxide nanoparticles, copper oxide nanoparticles is having interesting properties and uh, having wide applications such as in gas sensing, in lithium-ion batteries, in solar cells, and MRI and superconductor. It shows semiconducting properties. It is well known p-type semiconductor. Next, please. To synthesize copper oxide nanoparticle, first of all, we will prepare the neem extract. To prepare the neem extract, neem leaves were collected from our college campus and washed by tap water 2 to 3 times, and again washed by distilled water 2 to 3 times. After washing, left to dry for 10 to 15 minutes. After drying, the leaves were about 60 gram of neem leaves uh, are added in a 600 ml of distilled water and heated for 1 hour at 70 to 80 degrees Celsius. After heating, it is observed that the color of solution is extract is turned into yellow brownish color as shown in figure. And after cooling down, is filtered by filter. Next. Secondly, second we have to prepare copper acetate solution. To prepare it, simply the 10 gram of copper acetate solution is weighted and add in a mixed in a 250 ml and 100 ml of distilled water. Next, synthesis of copper oxide nanoparticles. To synthesize copper oxide nanoparticles, 500 ml of neem leaf extract and 150 ml of copper acetate solution is mixed in a beaker. After mixing, it is observed that the color of solution is turned into dark green color. And after some time, 2 to 5 minutes, the precipitate is settled down at the bottom of beaker. After that, the solution is filtered by one number of filter paper, and precipitate is washed by distilled water. After washing, the precipitate is left to dry for almost 24 hours in room temperature. After drying, the sample was crushed in fine powder and collected for characterization. Result and discussion. Our sample was characterized by two methods: UV visible spectra and XRD. First of all, first in UV visible analysis of sample is done in a wavelength range of 200 to 800 nanometers. The maximum peak was obtained at 213 nanometers. By comparing with the bulk material of bulk of copper oxide UV, it is observed that the peak is shifted to the higher frequency range as size is decreases of nanoparticles. In XRD analysis, by analyzing the XRD data of our sample, it is observed that the diffraction angles and for a diffraction angle to theta, the structure of nanoparticle is simple cubic crystalline structure. And by using the XRD, the size of nanoparticle is found to be 5.8 nm. Next. In conclusion, we can say that the method is cost effective, eco-friendly, and easy to done in any laboratory to operate. By characterizing our sample, the XRD analysis confirms the nanoparticle is obtained and the highest peak value is obtained at 230 nanometers, and the size of nanoparticle is to be 5.8 nanometer for first order peak value. Next, these are the references. Thank you.
You have research project assistant characterization of copper oxide nanoparticle using neem. You know, characterized for individual spectroscopy and exam. I have one question. What was the reference used for measurement of ultraviolet spectrum?
Ultraviolet spectrum. References.
It's all like particles of the spread of the plate. How do you measure the use this? The participants, if you have any questions, the session is open for discussion.
तर त्याला म्हणजे बॅटरीज मध्ये आणि सेमी कंडक्टिंग चांगल्या प्रॉपर्टीज दाखवतो आणि सुपर कंडक्टर जो असतो बाकी सुपर कंडक्टर पेक्षा तो जास्त टेम्परेचरवर सुपर कंडक्टिव्हिटी शो करतो. तर त्यामुळे जो सुपर कंडक्टर थँक्यू. जास्त मिळालं. नाही सर नाही केलं ते कारण रिडक्शन झालं तिथं म्हणजे आपल्या नीम एक्स्ट्रॅक्ट मध्ये जे हे असतात त्याच्यासोबत रिडक्शन
Thank you all the participants, and I would like to thank Dr. Abhijit Yadav sir and K.R. Nemade sir for judging the participants, and with the permission of jury, this session is concluded. Now lunch is arranged, so everybody is eagerly waiting for you there. Next session will be start after half an hour, so be ready.
हा नाही वेगळं वाटतं वाटतं याच्यात टाकून मीटिंग एंड झाला YouTube एंड होतं ना